All right, there we go. So we have two problems here that we want to take a look at. One is explicit and the other one is implicit. And I was looking over at your work on the pair deck earlier, and David, that is very packed on there. And I just caught my eye right now. I was like, wow, that's a lot of writing in there. And yeah, pretty cool stuff that you guys have written on there. Ava, I appreciate your circles. Looks good. All right, so let's take a look at the first one. That is a explicit problem. So I'm going to go ahead and move this one out the way so we can work on it a little bit later. All right, scoot you over a little bit further. You get over there. Okay, so let's take a look at this one first. Oops, I forgot to move you. Boom. All right, so let's take a look at you first right here. All right, I'm hoping you guys can see that there are two functions involved and they are multiplying with each other. All right, we have one function right here and I have a second function right here. And just because they're written next to each other doesn't mean that it's a inside function, right? That doesn't mean that this square root is inside tangent, right? I tried to draw the parentheses there to make it noticeable that tangent has an inside function of only 3x, and the square root function is multiplying with it. That's the second function that you have there. So noting that, you should hopefully see that this is a product rule that's going to be applied here. You have your f of x right here. You have your g of x right here. So we're going to do the derivative of the first times the second plus the derivative of the second times the first when we calculate this derivative. Okay? So breaking that down, though, each of these have the chain rule functions applied to them, right? You have an inner for the f of x function right here is going to be, the inside is going to be 3x. The outside is going to be tangent of 3x, right? Or tangent of some stuff. Whereas the g of x also has an inner, which is x squared plus 1, and it has an outer, which is some the square root function, but I'm going to write it as that as the power of 1/2. Okay, so calculating this derivative, right? Like I said, is going to be equal to the derivative of the first times the second plus the derivative of the second times the first. That's all that is. Notice that it's the chain. Notice that it's the product rule, and then apply the chain rule when needed. All right. So derivative of the first function is going to be 3 times derivative of tangent, which is secant squared of 3x. All right. That's going to be derivative of the first multiplied with the second function, which is just x squared plus 1 to the 1/2. But if you write it as the square root of x squared plus 1, that's perfectly fine. It's the same thing. Plus derivative of the second function, derivative of the inside here is going to be 2x times the derivative of the outside, which is 1/2 times some stuff to the negative 1/2 power, which is x squared plus 1. I'm going to slow it down here a little bit and pause there for a second. Did I lose anybody so far on any of the derivatives I've done so far? The derivative of the tangent function or the derivative of the square root function? Are you guys okay? If not, let me know, because I'm going to keep going. But again, this is all for your sake. I'm doing these problems just so you guys can see, right? Max, you're okay. Thank you for letting me know. I appreciate it. Anyone else? You guys are all right? I'm going to assume that you're all right if you don't type anything. I know you're not supposed to assume, but it's what I got to do. All right. And that, of course, just multiplies with f of x at the end, which is going to be tangent of 3x. And that's it. I would stop there. In fact, I would prefer it if you stop there, and I give the full credit if you stop there. If you use something like Photomath or Mathway, they simplify it, and their simplification gets weird. Like, not kind of weird, like it's really weird. So they make things that should be as simple as this, and they write it out like a little bit stranger. I don't know if you guys have ever used Photomath or Mathway. I have nothing against them. It's just the fact that in calculus, they don't work as well as they used to back in your IM1 classes or IM2 classes where, you know, it's like an easy solve this quadratic type of problem, right? So I just wanted to make sure you guys understand that. Don't use those programs when you're dealing with stuff like this. It's not bad if you understand what you're doing and you want to use it to check your work, but then at the same time, it's going to get really ugly. Can you go over the 1/2? Of course. This part right here, Max, right? The 1/2 to the, yeah, okay. So That's just the derivative of the outside of the second function, right? So I'm rewriting this square root as x squared plus 1 to the 1/2, right? And the derivative of something to the 1/2 power, right? You bring down the power, right? So when I take the derivative of this, this comes down to 1/2 times some stuff to the negative 1/2, right? It's like if I had the x to the third, the derivative of that would be 3x squared, right? You just bring the power down, yeah. And then since it's the chain rule, whatever is inside here is exactly whatever was inside to begin with. And it just kind of comes along for the road. If we were to do problems on Desmos, would we have to simplify? Oh, that's a tough one. That's a tough one. Yeah. That's a tough one. Okay, so Desmos I would use mostly just to plug in the original function just to look at its graph, I would say. I don't know if you would solve it on Desmos, really. So I don't think that's the case. I know on Delta Math, on Delta Math. Sorry. Okay, on Delta Math, sometimes it will ask you to simplify and sometimes it won't. And that's why I'm kind of like impressed with their software, is that when it doesn't ask you to simplify and you type it in, it will actually register this as the right answer. Like this monstrosity that I have here, which is, you type it in, you might have the order differently from mine, or you might have them switch with the plus signs, and Delta Math actually registers it okay. And it actually understands like, oh, it's the same. So I don't think you'll have to simplify if it doesn't ask you for it. It should work. And if it doesn't, and you have your answer, then it usually tells you what's the correct answer and what you typed in. Take a screenshot of it for me, and let me know. Like, I can just give you the credit for it, right? Does that sound fair, Emily? I hope that sounds fair, because I think, yeah, it seems to work out okay. All right, anyways, that's my answer, guys. Woo. Okay, awesome stuff. All right, that's explicit, right? Oh, wait. This would be marked wrong, by the way. Do you know why this would be marked wrong? It's not equal to y, guys. It's not equal to y. It's equal to dy dx or y prime. It actually does matter, by the way, what you set that equal to, right? Because then if you left it as y equals to that, that's saying, hey, this function's also equal to this function, which that's nonsense. So make sure you have the labels for it correctly as well. This should have been dy dx or y prime. It shouldn't have just been y. Why, you say? Well, just because. All right, so back over here. Number 2, explicit. No, I'm sorry. It was the first one. Implicit is what's going on right here. And a lot of you guys actually had the answer for this. So I'm thinking you guys are feeling comfortable now with implicit, right? Especially if you don't have to do chain rule with it or product rule, and you're just doing power rule, right? Because all that's left now is combining your derivative skills, which is taking, the power rule, and then combining it with your ability to solve for a specific variable, right? Equation manipulation, right? Some of you guys are realizing that. Hopefully you're realizing that. But if not, you'll see what I'm talking about. You're doing it without even noticing it, is what I'm saying. So since I'm looking for dy dx, that means I need to take the derivative with respect to x, And I'm going to do that for all these terms. So the derivative of x squared would be 2x, and then derivative of the inside would be dx dx. Now we, again, never really wrote that in the past because dx dx would just cancel. And you don't have to write it now. I'm just writing it right now just to help you see that this is actually being done for all variables. If you had a y, if you had a z, if you had a star, you had a banana as your variable, you'd have to put d star dx or d banana dx, depending on whatever variable you have, right? And in this case, dx dx is going to cancel out. Plus, the derivative of y squared is 2y, but again, it's 2y dy dx, derivative of the inside times the derivative of the outside, plus 3y squared dy dx. And of course, the derivative of 7, right, is 0. The derivative of 7 is 0. So moving right along, I have here the dx's cancel out, and I can move that 2x to the other side because the second step now is to get everything with the dy dx on one side and everything that doesn't have a dy dx on the other side. So while subtracting that out, I have here 2y dy dy dx plus 3y squared dy dx is equal to negative 2x. Now that I have all my dy dx's on one side, we take that old strategy of factoring out that common factor of dy dx. Right? So I have here dy dx factored out. I'm going to be left with 2y plus 3y squared is equal to negative 2x. And then once that's the case and you get that dy dx factored out, you just divide by whatever doesn't have a dy dx to the other side. So I'm going to divide by 2y plus 3y squared. And that's my answer. dy dx is equal to negative 2x over 2y plus 3y squared. Ta-da! But yeah, the reason why we don't learn this first, right, where we learned chain rule first, is because of that whole idea of taking the derivative with respect to a specific variable. Is the chain rule applying to things like y squared, right? Is the thing that's applying there. So now you have to actually take note. What are we taking derivative with respect to, right? And what variables are we looking at, right? I've been dealing with x's and y's here, but it works for any given types of variable that you might be dealing with. You could be dealing with s's and t's, q's and r's, betas and r's as well. All of those things, right? All of those things. So just keep that in mind when you guys are looking at that. It's the same concept. It's just the letters might change around, right? So don't freak out on that when you do that implicit differentiation. All right, let's keep going here. So I kind of want to move on, but I feel like we should do a couple more examples because we haven't done a second derivative for implicit yet, nor have we evaluated our implicit derivatives yet. All right, so let's take a look at some of these things and see how crazy this can get, right? So let's keep going here. We're continuing with our implicit differentiation, and we're going to do so for the second derivative, right? So let's say I was asked to find, right, y double prime, which is the second derivative. Now, they might not write it like this. They might write it as d2y dx2. The reason for that notation, by the way, is because you're taking the derivative with respect to x twice to your original function y. This is how they usually word it. It's either y prime or d squared y over dx squared. I just say second derivative. It's not as lengthy as d squared y dx squared. But the reason is, if you have your function y, right, and you take the derivative with respect to x once, that's how we end up getting dy dx, right? And if you take that dy dx and you take the derivative again with respect to x, do you guys see it? In the bottom there, you have a dx written twice. That's why they write it as dx twice. In the top, you have the derivative written twice. That's why it's d2, and it's of y. It's technically d2 dx2 of y. That's where this is coming from, okay? This is where this is coming from. So it's just that notation right there. And then if you take the third derivative, it will be d3y over dx to the third, right? And again, we don't read it out like that. We just say the third derivative of y with respect to x. This is going to be the second derivative of y with respect to x, right? With respect to x. So let's take a look at a problem here. Let's go with this one right here. Let's say I was asked to find the second derivative of x squared plus y squared is equal to 4x. Is equal to 4x. So you guys can work along with me on this one? All right, you can work along with me on this one. So for the second derivative, first things first, you got to find the first derivative, don't you? All right, so let's go ahead and find the first derivative. So looking at this, we're going to take the first derivative with, again, respect to x, with respect to x. So derivative with respect to x, okay? And do this for both sides of the equation. So on the left-hand side, I'm going to have x squared. That's going to be 2x dx dx. I'm not going to write it this time, but just know that there is a dx dx there that cancels out to a 1. Plus 2y, this one needs to be written down because it doesn't cancel out, which is dy dx. That needs to be there, right? And this, of course, is equal to the derivative of 4x, which is just 4, right? just the constant. It's just the coefficient of x, which is just 4. How are you guys doing so far? You guys okay? You guys all right? Have I lost anyone yet? I think you're doing all right. All right, check this out. Solve for dy on one side, get everything that doesn't have a dy dx on the other side. So subtract the 2x over to the other side. I'm going to have here 2y dy dx is equal to 4 minus 2x. All right, 4 minus 2x. Divide everything by 2y. And I end up with dy dx is equal to 4 minus 2x over 2y. But again, you can simplify by canceling out the 2's if you want, and you could write this as 2 minus x over y, right? And traditionally, we'd be done there, right? Normally, we'd finish right there and just say, ha, we're done with this problem. We found the derivative. We found dy dx with respect to x there. But it's asking us to find the second derivative. So this is what I'm going to do. I'm going to go in here now and take the second derivative of this. And this is me just doing d dx a second time, right? A second time. So check this out. D dx of dy dx is actually going to give me d2y over dx2, which is what we're looking for, okay? But hopefully you guys can see on this side now, when I do this derivative, what rule is going to be applied here? What rule is going to be applied here? What do you guys see? Can I just take the derivative of that? Is that okay? Quotient rule. Monica, Brian, yes, that is perfect. You're going to be applying, Gracie, the quotient rule here. And my low function, of course, is my y, and my high function is my 2 minus x, right? Max got in there as well, quotient rule. Yes, you are correct. So to do the quotient rule here, I need to go low, which is y, d high, the derivative of 2 minus x. Calvin dividing rule. I mean, yeah, that's technically true. It is the dividing rule if you're going to say multiplying rule. No, wait, we don't say multiplying rule. We say product. All right, anyways. So low is the y, d high is -1, minus high, 2 minus x, d low. Now, what are you going to write down for the derivative of y? That's the tricky part that you need to hopefully pay attention to. It is 1, but it's 1 what? There's more to it. Because remember, we're taking the derivative with respect to x. We're taking the derivative with respect to x. So the derivative of y with respect to x. Yes, you're right. There's going to be a 1 involved, but it's 1 what? It's 1 dy dx. That's right, Emily. It's 1 dy dx. This is the derivative of y with respect to x. It's not changed. Nothing has changed on these problems. You're still taking the derivative with respect to x. Yes, Oscar, Monica, I just saw that right now. Yes, you guys all got it right. dy dx divided by, right, divided by low, which is y squared. And normally I'd say, hey, we're done. We'd stop here and you're good to go. But you can't have your derivative, your second derivative, in terms of your first derivative. It's not normal, right? So what we have to do is replace the dy dx with what we know it to be already equal to. Do you guys see what dy dx is already equal to? What is dy dx equal to? Hope you guys see it. It's the 2 minus x over y. So I can replace that dy dx. Never mind. Yeah. So yeah, you can replace that dy dx with the 2 minus x over y. So I can rewrite this here. d2y over dx2 is equal to, right, y times -1 minus 2 minus x times 2 minus x over y all over y squared. And again, you could leave it like that. But if I asked you to do a third derivative, I wouldn't do a third derivative there because that's just going to look ugly. You're going to have a product rule with a quotient rule inside. I would simplify it if they ever ask you to do a third derivative, which again, they might do that. So you need to practice a little bit of algebra for cleaning up if you need to simplify, if it's a multiple choice question, or if you need to do a third derivative. If a free response question just asks you to find the second derivative, you can just leave it there. All right, you can just leave it there. You don't have to go any further. But if they need you to match it with a multiple choice question, then you need to simplify to see which one does it match up to. Right, so for this one, let's go ahead and simplify this out. I'm going to rewrite this so it looks a little bit cleaner here. So let's see here. I'm going to have here negative y. This is all over 1, I should say. I can multiply this out. I can FOIL that. So this is going to be y minus, right? And then on the top here, I'm going to have x squared. Negative x times negative x is x squared. Negative 2x. Negative 2x is negative 4x. And then 2 times 2 is plus 4, I believe. And this is all over y. And this is all over y squared, right? Simplify the top fraction. This monstrosity here, I'm going to simplify that by combining the two fractions together by getting a common denominator. Common denominator is going to be y. So I'm going to multiply top and bottom of the first y right there by y. So it's going to be y and y squared, right? So that they have a common denominator, so I can subtract these two together, right? So this is going to become negative y squared minus x squared plus 4x minus 4. I'm distributing the minus sign here and combining it with the y squared in front since they both have a common denominator of y. So this is all over y, but this is, again, all over y squared. That's an ugly fraction bar. What I'm doing right now is just simplifying this fraction, right? I'm making this complex fraction into an easier fraction to deal with. Get out of here. I don't want to. Okay. All right, there you go. Okay. Now, you're almost done. This last part right here. You have a fraction over a fraction. You would keep flip change and you simplify this all out. This would simplify out to y squared minus x squared plus 4x minus 4 all over y cubed. And this is your d2y dx2. That's what that would simplify to. And again, you don't have to do it unless you were doing a multiple choice question or, again, you were asked to take a second derivative. I'm sorry, a third derivative. So you have to do it again. But looks good there. You guys okay? How do you feel? No, you're not okay. Where did I lose you at, Oscar? Well, actually, first things first, are you okay with the derivative part? Yeah. So I don't think you're the only one, Oscar, who's a little uncomfortable with the algebra I just did here from here to here. All right, so let's mark this down. Let's mark down the steps here. So step 1, right, was replacing the dy dx with what I know it's equal to. Step 2 was FOILing it out. Step 3 was combining the fraction. Oscar, where did I lose you at? Step 1, step 2, or step 3? We can go from there. Step 3. Okay. So let's do this on the side. Side note. I'm looking only at the numerator on a side note. I have here minus y minus x squared minus 4x plus 4 over y, right? So if I have this right here, right, and I want to combine them into one fraction, I multiply by a common denominator, right, to the other fraction. So I'm going to multiply top and bottom here by y, right? And that y, negative y is the same as negative y over 1. So I'm doing this to the first one so I can get a common denominator so I can combine the fractions together. So when I do that, and I combine those, I multiply this out, I get negative y squared over y minus x squared minus 4x plus 4 over y. And since they have a common denominator, I can combine the two fractions together, and what I get is negative y squared minus x squared minus 4x plus 4. Okay? Then all I did was distribute the negative sign that's right here, after combining the two fractions together. That's how I ended up with step 3, which is negative y squared minus x squared plus 4x minus 4. It's still all over y, and this is, of course, still all over the y squared. So this right here is what replaced into here. These guys right here. Does that make sense, Oscar, or is that still confusing? Yeah? Okay. Awesome. Awesome, awesome. All right. That's the second derivative in a nutshell. So it is going to take practice, guys. Don't think that you're going to get this in one try. It is not something that you can pick up in one try. And I wish we had more time to practice it in class, but I need to show you how to evaluate this as well. So just a heads up, when you start doing the homework, I suggest you start doing the homework. I will have this homework for implicit posted. I hope I do it today. I said I was going to do it on Tuesday for my stats class. I'm just realizing right now that I forgot to do that for my stats class. Lovely. All right, so yeah, so all I'm saying is practice, 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 right? Get some practice in there, and if you're practicing and you don't understand it, stop by my office hours, guys. You always are welcome to stop by and ask for help, which is something I suggest you do. Okay? Please. Please do. Please do. Okay, so let's keep going here. Let's do another one, but let's say I was asked to evaluate. Let's say I was asked to evaluate, okay? I want to get one that's a little bit easier, so give me 1 second here. I'm going to look in your book and see if I can find one that's easier than one that I'm going to make up, because if I make it up, it might not be pretty, you know? It might not be pretty. So I want one that's pretty. Okay, so let's say I was given a problem that looks like this: y cubed plus y squared minus 5y minus x squared equals to negative 4, right? And they asked me to find the slope of the tangent line at, what's a good point? Let's go with this. Let's go with at, here we go. Let's go at 2, 0. At 2, 0. So, slope of a tangent line. What's the first word that should come to your mind when you hear the word slope of a tangent line? What is it? Derivative. Very good. Very good, Monica. Very good, Max. You ever hear slope of a tangent line? You need to think derivative. You ever see the word derivative? You need to think slope of a tangent line. Right? Your derivative is a function that will tell you the slope of the tangent line at any point on the curve. You just need the actual function, and you actually need the point. Now, when we did things explicitly, right? When we did things explicitly, you just needed an x value. You did not need the y value, because when it was explicitly written, your function, right? Your equation was an actual function, and it passed the vertical line test, right? Meaning at any x point, you only had one y point. Implicit functions, I say that loosely, implicit equations aren't really functions anymore, right? They still graph stuff, but they graph multiple outputs for your inputs. So your y is not technically always dependent on your x. You're gonna have multiple possible outcomes for your y's, and I'll show you what I mean in a second. But let's just actually go into this and actually do the calculations here. Okay. So traditionally, right, whenever they ask you to evaluate at a point, I love these things. You don't need to like go through the things of factoring and solving it. You can actually just plug in the point and then solve it afterwards. Let me show you what I mean. So let's say here, I was asked to find this derivative, right? So I take the derivative of both sides, right, with respect to x, right? With respect to x. So I have here 3y squared dy dx plus 2y dy dx minus 5 dy dx minus 2x dx equals to 0. And again, if we were just doing it the old-fashioned, the way that we were doing earlier, it's not that much more difficult, right? It's the same thing as before. We would add the 2x over to the other side, right? I end up here with 3y squared plus 2y dy dx minus 5 dy dx equals to 2x. Factor out a dy dx. I think you guys are going to catch that eventually. I forgot the dy dx on that 2y squared. All right, factor out a dy dx. 3y squared plus 2y minus 5 equals to 2x. Divide both sides by that polynomial right there, and I get dy dx equals to 2x over 3y squared plus 2y minus 5. Now, they asked us to evaluate this thing, right? They asked us to evaluate it at 2, 0. And what that means is plug in 2 for your x, plug in 0 for your y, and what do you get? So this is going to be equal to 2 times 2 over 3 times 0 squared plus 2 times 0 minus 5. So my answer here is going to be a slope of my tangent line should have my tangent line should have a slope that's equal to 4 over negative 5. What I was trying to say earlier was that when you do these types of problems, sometimes some people find it easier to just plug in your x and your y right after you take the derivative. So some people actually plug it in at this step right here. Once they take the derivative, they just plug in their x and the y values and then solve for dy dx after they plug it in. So they would do this and say, oh, it would be 3 times 0 squared dy dx plus 2 times 0 dy dx minus 5 dy dx minus 2 times 2 is equal to 0. And they'll solve it this way instead, and you'll get the same answer, right? The zeros there cancel, the zeros there cancel, and this is going to be left with negative 5 dy dx is equal, negative 2 times 2 is 4. So that's minus 4 is equal to 0. And then when you solve this, you see this is a little bit easier to solve for dy dx than having to solve the other one because you plugged in all the numbers. There's no more x's, there are no more y terms. And you can just solve this here algebraically, just like you did it over there, and you get 4 over negative 5 as well. And you get the same answer. So I leave that choice up to you. Do you guys want to do it implicitly like we've been doing and then evaluate it at the end? Or do you want to evaluate it right after you take the derivative? And when you're evaluating at a point, it just makes it so much easier. Like for some people, they prefer plugging in it right there. I prefer solving it all the way out to here and then plugging in, because just from practice alone, like I've seen a lot of problems, like like my test problems, you always see like, hey, knock me. There's only like 6 questions, but there's a 6A, 6B, 6C, and 6D. Because you guys love that, right? Right, multiple parts, right? You love that, yeah. So in 6A though, they might ask, what is the dy dx? So they might be asking for this particular thing, and then part B might ask, what is the derivative evaluated at this part? So you get to kill 2 birds with 1 stone if you go this way, right? But if they only ask you to evaluate at the point, there's nothing that you won't get marked wrong if you plugged it in directly into where you take the derivative of both sides with respect to x, right? If you plugged it into here, I swear I hit the highlighter. If you plugged it into this part of it with your point and you get your answer of 4 over negative 5, that's perfectly fine. Okay? Anyways, I wanted to show you something real quick. So I can't ever get past this without, showing you Desmos, right? But I mean, I technically could do it on your TI calculator too. But Desmos, free app, has no ads, takes up barely any space on your phone if you download the app. It's pretty good. It's pretty good. All right. Did I write this down right? Here we go. So take a look at this graph right here. You guys see this graph? So, is this right? Did I mess this up? I think I might have messed this up. Hold up. Either or Desmos is graphing it wrong. Give me 1 second. That looks good. Oh, it's a -4. That's important. There we go. There we go. Okay, I was like, that's not the right shape. Okay, so we're looking at the point 2, 0, right? And again, in the past, I would just give you, hey, evaluate this at x equals 2. But look at where x equals 2 is. Look at where x equals 2 is. X equals 2 is right here, right? And it passes through this function at 3 different points. It passes it through here, here, and here. And if I'm asking for you for the slope of the tangent line, I don't know if you're going to give me the tangent line at this point, which is a negative tangent line, and we found out is negative, right? Negative pi over, I'm sorry, negative 4 over 5, right? Or if you actually calculate the slope at this point instead, this is a positive slope, but that's a different point. You see that? That's at 2, 1.791. So it actually does matter, right, where you're trying to find the derivative at. So keep that in mind. When you do it implicitly, you not only need the x value, but you also need the y value to calculate. And you'll recognize that actually when you look at your derivatives implicitly, because most of your derivatives, once you solve it implicitly, will have a y value inside. So when you ask to find the derivative and you only plug in the x value, you're going to be like, oh crap, I need the y value as well. And you have to go back and find it either by plugging in the x value and seeing, oh shoot, which one do you need? Yeah, and so on and so forth. Anyways, let's wrap this up. I want you guys to try one problem before you go, right? One problem before you go, and I want you to evaluate it at a point for me. So let's go ahead and take a look at one more. I'm going to clear the pair deck, and we're going to have you do one more problem on there. Oh, whoa, I saw a bunch of drawings on there. Hold up. Someone was drawing like rainbows and whatnot. I gotta go back and find it. All right, let's go back. So let's do this example right here. That's a mean one, but let's do it. You guys can handle this one. So let's go with this one right here, and you guys can give me the answer for it. Can you find, yeah, let's go. So here's the equation. 2y to the 4th minus y cubed x squared plus 4x cubed is equal to 5. Can you find the derivative at, we'll find the derivative first. Let me see if I can figure out a point that would be nice for you. Give me 1 second. Whoops, no, I don't want to go there. Give me 1 second here. I'll tell you where the point is. So get started on that. X squared is 4x cubed equals to 5. Oh. Can't even click on this thing. There we go. Okay. I can't even get you a nice point on this one. It's so wiggly. Jeez. there's not a nice point anywhere. Oh, they're all at like weird fractions. Oh, Desmos is freaking out to the point where I can't even get a point on here. Interesting. Interesting. Huh. Not a single point. All right. Well, I made that a little too difficult to the point where it just isn't going to actually be able to evaluate it at a point. Whoops. Oh, well, it's fine. Not fine. I wanted you to actually evaluate at a point. Why did I make one so complicated? Hold up. Have you guys already started on this? No, you haven't, right? Let me make it a little bit easier. Hold on a second. Why can't I click on anything on here? X equals to, let's say, 0. I didn't have my problems ready for this one. Well then, let's make it a little bit easier anyways. Hold up. Why are you not working anymore? What? I can't even click on it. Well, that's still fun. Like, that one works, but... All right, well... Stop doing that problem for a second. Stop doing that problem for a second. I looked at that one, but no, let's just stop there for a second. Hold on. Okay, we got like 5 minutes. All right, let's see if we can try this one. And then I'll leave it open so you guys can turn in the pair deck afterwards. But let's try this one. This one, I have the answer in the book, so I'm going to go with theirs. Yeah, let's go with that one. So find dy dx at the point 3, 1. And I think this is where we're going to have to continue next time as well. But that is a problem that does work, and it does cross at that point. I was trying to figure out the point for the other one, but I could not find it. It was not working with me here. So let's go ahead and double check that this one works before you get into it. But it should work because the book says it has it at this point, and I'm hoping the people who did this book did it correctly. Let's see here. Close 100x. Yeah, there we go. Okay, that looks a little bit better, and I'm looking at 3, 1. Apparently, Desmos doesn't like me typing in these implicit forms and trying to find the points. So yeah, there you go. See if you can find the derivative at 3, 1 for this problem. I'm gonna leave the pair deck open because I don't think you're gonna have enough time to finish it. There's about 4 minutes left in the class. So you can finish it later on by the end of today. It should lock out at around like 5 today. So just remember to do this one. It's not really homework, but it is just something that you should try, and I need to see where you guys are at. But yeah, see if that works out. And I'm sorry if you're watching this as a recording and you saw me stumbling around for like 4 minutes. Hopefully you didn't sit there and just listen to me ramble on, and instead you like fast forward. Hopefully. All right. That's going to be for that. There is a chain rule on this one, yes. There is a chain rule on this. All right, we only have a minute left in this class, and I'm not gonna have enough time to explain it, but hopefully you guys are able to try it. I'm leaving the pair deck open for you to try, and it saves automatically. So once you finish, you can just close it. It should have it saved on there for you. And I will be taking a look at this later today. When we come back next week, I will go over this with you along with, I think, finishing up this section. I should have the homework for this posted up later today for you to do some of the more practice of these problems, because it takes practice to do these types of problems. And yeah, I think that's going to be it for today, guys. For homework, do we choose a column? Yeah, for the 3.1 part 2 on the worksheet, it says to select a column there. So when it says select a column, you just do all the problems in one of the columns, right? So there's 3 columns in total. Don't do the whole worksheet. That's like, it's not that difficult, but just pick one of the columns and only do those from top to bottom. That's all 3.1, by the way. That's all chain rule, not implicit. So the implicit homework will be up later, and I'll post that up later today. Yeah. So it's about 10 problems in the column. That sounds about right. All right, guys. That's it for me, guys. Have a good rest of your day. Have a good weekend. I will not see you until Tuesday next week. All right. Stay out of trouble, guys. Stay out of jail. Don't get pregnant. All right. So long, guys. Farewell.